So like I said, what we want to be able to do now is represent atoms in a picture type fashion. All right. So you are definitely going to need your periodic table for this, and I'm going to describe a little bit about the way we draw Bohr diagrams, and then we're going to draw a bunch of Bohr diagrams up to the first 20. I'm hoping we can get that done, and then we're going to learn about some properties. Actually, who's kidding who? I'm going to teach you about the properties eventually, and then we will ultimately be able to draw these things. Some textbooks, including ours, call these Bohr/Rutherford diagrams, and that's because it includes the nucleus as well as the electrons in their orbits. So recall that Bohr said that the electrons would exist in certain rings that contained so many electrons, and that the further you got out, the higher the orbit, the higher the energy, and the farther away it was from the nucleus. Let's write down some of that information. No need to write Bohr diagrams again. Can I move this thing? Oh, I can. Good. Oh, I wanted to do a little bit of a review of counting particles, but I'll save that for tomorrow. So Bohr diagram represents the arrangement of the electrons in the energy levels and the particles in the nucleus. Last day, we learned how to determine the number of protons, the number of neutrons, and the number of electrons. We need that information to draw Bohr diagrams. In grade 9, they normally have you put in the protons and the neutrons in the nucleus, but we're going to do a shortcut. Because I'm sure Jessica loves shortcuts. No, I'm just joking. I shouldn't start so early. She does like shortcuts. And because we're kind of squeezed in for these next 2 days, a shortcut doesn't hurt. Oh, trust me, I try to give you guys as many shortcuts as you can when it comes to this. I'm a firm believer of, yes, learn the content, but if there's a good way to summarize it, then and to make it shorter, then by all means, that's what we want to do. Place electrons in an energy level until it is full. I'll explain what I mean by that. Once the energy level is full, electrons are placed in the next available energy level. Now, I am going to have you fill in a chart here for a moment, but I'm also going to get you to draw some pictures. So I wasn't sure how I wanted you to do this. So maybe don't put this in a table. Put energy level, put the number of electrons, but I'm going to draw some stuff here, okay? All right? So at this point, I want you to put energy level, number of electrons, the first energy level. All right? And I'm actually going to write down the number of electrons that go in the first energy level, and then I'm going to show you the way we represent it. Now, number of electrons in the first energy level. 2 electrons go in the first energy level. And you might think that this is arbitrary, but it isn't. The mathematics out of my big chemistry book that I've shown you before, the mathematics determines how many. It is not a coincidence. How many elements are in the first period on the periodic table? Yep, 2. That is not a coincidence. The shape of this periodic table is determined by the number of electrons that go in each of the orbits or rings. Okay? I'm going to come back to draw some more things about this first energy level, but let's move on to the second to see the trend. How many electrons do you think go into the second orbit according to my logic? How many? Yep, 8. How did you get that? You counted across. The periodic table will tell you how many electrons go in the orbits. 8. Again, I want to draw a picture here to represent what's happening, but let's just keep going. In the third orbit, how many electrons will go into the third orbit? Danton? 8. You counted 8 across, didn't you? Good job. 8. Now, strange things happen in the fourth. You're going to count across. You're going to get a number. But this isn't really the way the atoms behave. Goofy things happen in the transition metals. If you continue on and take grade 12 university chemistry, which I hope you do, right, Chloe? W at the back, you're going to take it. Good stuff. Then I'll explain why it doesn't work that way. But that's okay. We can write it down. How many do you think would fit in the fourth? What do you got? We counting there? Yep. 18. Now, I'm going to leave that blank. It really isn't 18, but we're going to stop at calcium anyway. Let's put 18, and then I'm going to put a big question mark underneath that, because there's complex things happening down at the bottom of the periodic table, and we're just introducing you to the beginnings of this. Okay? All right. Now, how do we draw this? Let's go back to the first. We draw a circle to represent the nucleus. All right? And we put the number of protons in that nucleus. The number of protons. Okay? And in grade 9, they often make you calculate the number of neutrons as well, and put the neutrons in there as well. But you know what? The neutrons have nothing to do with the way chemistry behaves. The neutrons are there just to make things heavier or lighter. So the neutrons aren't that important. So we're not going to put the neutrons in there. We're not going to do the math. It's going to be really easy. That's our shortcut. Now the electrons in the orbit. We draw rings to represent the orbits. All right? Now, some grade 9 textbooks will have you put the 2 electrons as far away from each other as possible in the orbits. And they like it to be logical. Why do you think 2 electrons would get as far away from each other as possible? Yep. Yeah. The like charges repel. But, and I think I might have mentioned this to some of you, electrons are spinning. They're spinning like a basketball on a basketball player's finger. And when the electrons spin, they create a magnetic field. Now, this is way above your pay grade in the science world. This is okay. It means that when they get together, they sometimes like to pair up a little bit because they're attracted to each other a little bit like 2 magnets can be attracted to each other. So they do like to get away. But if they have to, they will form a little pair of electrons. I like to think of it like siblings, right? Think of your sibling. You sometimes don't like your sibling, and you want to get away from them, but then Christmas comes around, and they give you a gift you didn't expect, and oh, you do love your siblings, oh, so you do get together. Similar idea. Now, let's think about houses and siblings. In the first orbit, there's only one bedroom. There's only one bedroom for the siblings, which means when the first electron or the first kid comes along, nice, get my own bedroom. Good times. But when a sibling comes along, if there's only one bedroom, you gotta share the bedroom. Sucks. Not so great. So in the first orbit, the first electron goes in, nice, no siblings. Second sibling comes along, crap, I got to share the bedroom. So they end up paired together. All right. In the second orbit, so I'm going to make my nucleus a little smaller, so it's a little closer in. Here, I've got a couple of electrons in the first orbit. We represent them by dots. There they are. I always put them at the top, but it doesn't matter where you put them. There's the first orbit filled. Now we're talking about lithium, beryllium, all those guys in the second. Second orbit. Put it out there bigger. Again, this time, because there's more electrons, the family's getting bigger. The next floor on the house has 4 bedrooms. Each bedroom can hold 2 electrons. They don't like to be together, but if they have to, they're okay with it. So, in the second orbit, there are 4 bedrooms. 1, 2, 3, 4. And when we start filling electrons into those bedrooms, those first siblings say, I'm not pairing up, not until I have to. So, first one goes into a bedroom, nice. Second one gets its own bedroom, nice. Third one gets its own bedroom, awesome. Fourth one gets its own bedroom. But when the fifth one comes along, they got to start pairing up, okay? And it's this pairing up that's really important to explaining the way chemistry happens. And in many textbooks, maybe even ours, I didn't look at it that closely, they simply spread them all out. But if we don't pair them up, we can't think about the way chemicals are formed. That's going to be same with the third orbit. And like I said, with the fourth, it gets a little goofy. So again, if I were to draw with the third, I draw a little circle in the middle. That's my nucleus. Again, I've got my 2 in the first orbit. I'm now to the end of the second orbit, which means we've done it like this. 1, 2, 3, 4. Now we got a pair, 5, 6, 7, 8. So that's a full orbit now. That floor of the house is full. So if there's going to be more electrons coming along, you build another floor on the house. And also 4 bedrooms on that floor as well. 4 bedrooms on that floor. Again, electrons don't really want to be that much together, like siblings. Okay, I'll kind of hang out with you if I have to, but I'd rather have my own bedroom first. Okay? And then, like I said, in the fourth, things get really goofy, and we're not going to worry about that. Okay. So let's, question? Correct. Divided by 2, because they'll pair up, but they'll never make groups of 3. Electrons never get together as groups of 3. They only pair up. Correct. If it's an odd number, then that's fine. It means you might have a couple of pairs and then some extras, some singles. Okay? All right, let's start drawing a few of these. Yep, question. Yep. So that's the second row filled. In other words, we got across here to neon. Yep. That's from the very, very first orbit. Correct. They stay there. We stack them up as if we're building the floors of a house. Except it's a funny shaped house. It's like an upside down triangle house because there's only 1 on the first floor, 1 bedroom, and there's 4 bedrooms on the second floor and 4 bedrooms on the third floor. And technically, you could think that there's 9 bedrooms on the next floor. You know what I mean? And it grows kind of goofy. Okay? All right. Let's start drawing these things. Now, here, let me show you a sheet that we have on Google Classroom. If you go to Google Classroom, all right, I have a sheet that says here, and you can fill it in on this if you'd like, but it says down here, Bohr Diagrams, and it's essentially a chart where you can try to draw all those Bohr diagrams, because we're going to draw all the way down to calcium, okay? I have that chart here. You'll notice that I have it here on, let's clear this away. So I have it there, okay? And if you want, you can open that up and you can start filling that in, or you can just draw it in your notes and then go to it. I'm going to do some random ones here, okay? So you can fill it in on that chart, but for now, I'm going to go back to my PowerPoint and I'm going to do hydrogen. Okay? Yep. If you want a stylus, you can come and grab one. In the end, we're going to be drawing all the way to calcium, or you are in a moment once you see the trend. But I'm going to just draw it here on the board. Okay, how do we do this? Number one, locate your atom on the periodic table. There it is. I'm going to put a circle in the middle to represent the nucleus. And I'm going to put just the protons in the nucleus. So we don't have to subtract from the mass. Remember, we were subtracting from the mass to get the number of neutrons? We don't need that step. So, atomic number 1. How many protons in the nucleus of a hydrogen atom? Yep. 1. Right, plus 1. I've seen some people say, number of protons, 1. Number of neutrons. Well, we're not doing the neutrons, and I don't want to write the little number sign, plus 1. That's the charge of that nucleus. Draw the first orbit. There it is. How many electrons does hydrogen have? Nope. 1. Because remember, it's the same as the number of protons, because the charge is neutral. So atomic number 1, 1 proton plus 1, 1 electron. I put it in the orbit with a dot. There it is. That is the Bohr diagram for hydrogen. It has 1 orbit, and it has 1 electron. How are we doing? Okay. Let's move on to helium. So if you're drawing it in the document, awesome, you're sliding over to the other side, to this position. I'm just going to draw it on the board. I draw a circle for the nucleus. How many protons? What's going in the center of this dot? What's going in the center? Harrison, what do you think? Plus 2. I draw the first orbit. How many electrons does this have? 2. How many electrons does the first orbit hold? 2. How many bedrooms are there? 1. So I'm going to put them right beside each other. Many grade 9 teachers will say, get them far apart from each other, but that's really not the way they exist. They exist in the same area because they're siblings who are repelled, but they're good friends too. Okay? All right. This orbit is full. Let's look at lithium. I've now gone to the next orbit. Circle for the nucleus. How many protons in the nucleus? Plus 3. There's a trend here. See the trend? Plus 3. How many electrons in the first? Well, how many electrons in total? 3. How many in the first orbit? Yeah?
3, but 2 in one room and one.
Nope. There's only 1 room in the first orbit. So 2 in the first orbit. That orbit is full. The first orbit only has 1 bedroom. I'm done that. I need a second orbit. How many more electrons have I got left to put in here? What's going on? Yep. 1, and it can go here. Awesome. It really doesn't have to be at the top, but I always build it at the top. I build it like a clock, 12 o'clock, 3, 6, 9, and we work our way around. So, first orbit is full. We're now into the second orbit. Notice something. What period is lithium in? That's the horizontal row. What period is it? How many orbits does lithium have? Not a coincidence. What period is hydrogen in? How many orbits does hydrogen have? Fun. Let's do another one. Beryllium. Okay, and we're not moving too fast here. I'm slowly building you up. Go ahead if you know what you're doing. We put a circle in the middle. First orbit. How many orbits will beryllium have? Before we even think about counting things, how many orbits will beryllium have? 2. Why? It's in the second period. We can work backwards from its location on the periodic table to figure out the Bohr diagram. There's a link between these two things. We've been counting up to this point, but now we can even use its position to learn how to draw it. What's the charge on a beryllium, Danton? +4. How many? That's okay. How many electrons in the first orbit? Nope.
2.
There's only 2 in the first orbit. And now how many have I got to deal with in the second orbit? 2. And they're going to stay away. They can have their own bedrooms now. Again, some teachers would say, put it on the opposite side, but I always go from 12 o'clock to 3 o'clock. It's the way I like to draw it. All right. Let's notice another trend here. How many electrons does hydrogen have in its outermost shell? Go back to hydrogen. It only has one shell, so that is its outermost shell. How many electrons does it have? 1. How many electrons does lithium have in its outermost shell? Go to lithium. We just did it. Look at its outermost shell. How many electrons does it have? 1. Not a coincidence. How many electrons do you think sodium will have in its outermost shell? 1. Not a coincidence. How many did beryllium have in its outermost shell? 2. Look at the group number. 1, 2. Click. Now, look at what I did. I jumped all the way down to sodium. That's fun. Well, I wanted to see whether we could figure out the trends, see if we could figure out how to draw it. We can draw it 2 ways. We can draw it by counting everything up, or we can think about where it is in the periodic table. All right? I'm going to do it actually both ways. It doesn't really matter. I'm going to start with a little picture on the left. You only have to draw it once. What's the charge, or how many protons is there in a sodium atom? How many protons in a sodium atom? Yep, Jack? 11. Atomic number is 11, which means it's also going to have 11 electrons, plus 11. Well, how many automatically go in the first orbit? 2. So I'm going to draw them in. Notice I'm not even counting up to 11 yet. I'm just starting to build it. How many electrons go in the second orbit? How many? 8. 8 go in the second orbit. 1, 2, 3, 4. Now they got to pair up. 5, 6, 7, 8. How many electrons have I used at this point to get to that point? Yep, Rachel? So how many more have I got? 1. The second orbit is full. I must go to the third orbit because it's full. And remember, the period number is going to tell me how many orbits. And I'm going to put a 1. I believe we just predicted that sodium should have 1 electron in its outer orbit. That is correct. That is good. Okay? Let's pick one more at random, and then I'm going to let you finish off the chart. So, one more at random. The only thing is I've got to keep it within the first 20 because strange things happen down here. We're not getting into that. So let's just choose phosphorus. All right? Phosphorus. Now let's see if we can figure out some trends before we even get drawing this. What period is phosphorus in? What's the period number? The horizontal row. Yep. 3. How many orbits will phosphorus have? Just 3. Correct. 15. I don't think there's going to be 15 electrons. How many electrons were in the outermost shell of sodium? 1. What do we predict for magnesium? 2. We're going to ignore this part. What do you think it would be for boron and aluminum? Rachel? 3. Carbon and silicon. 4. How many should be on the outer shell of phosphorus? 5. Ignore that 1, and that'll tell you. Let's see if it works. Phosphorus. How many protons in the nucleus? What's the atomic number for phosphorus? What do you see in there? 15. It's the big red number. You bet. 15. Plus 15. All right, so we need 15 electrons, right? How many in the first orbit? 2. 1, 2. How many in the second orbit? Rachel? 8. 1, 2, 3, 4, 5, 6, 7, 8. How many have I used so far? I've used 10. How many have I got left? Rachel? 5. Third orbit can hold 8, so that's good. I'm going to fill in my bedrooms. 1, 2, 3, 4. Gotta start pairing up now, right? I got too many kids. 5. How many electrons in the outermost orbit of phosphorus? Rachel? There was 5, just like we predicted. How many electrons would be in the outermost orbit of argon? Any ideas? Yep. 8, correct. Finish that chart right now. Take about 10 minutes to finish that chart, and up to calcium. Okay? Take a little bit of time to finish that chart up to calcium, and then I've got a little summary note that we're going to do, and I'm going to pause the video. I'm going to pause. I'm sure you're doing a good job. I checked around. Most of you are putting things together very nicely. But counting all of these protons and then counting the dots, it's okay, but the table tells us everything. The periodic table is your friend. It tells you where the electrons are, and therefore we can build an atom. And when I say build an atom, not like we're actually putting atoms together, but build our picture of an atom from its position on the periodic table. And that's the better way to do it. This counting business, counting all these electrons up, you know, let's say you're doing calcium and you're counting up to 20, that's a mess. But there is a quicker, easier way. So these are the trends that I asked you to think about and look at. Elements in the same period have the same number of energy levels, or rings, or orbits. So hydrogen and helium, 1 ring, 2 electrons. Anything in period 2, from lithium over to neon, 2 rings. First one full, because we've gone past it. Second one, wherever you are in there. 1, 2, 3, 4, 5, 6, 7, 8. So therefore, the period number tells us the number of rings or energy levels. Now, this is also true for the ones way down at the bottom, but their energy levels are so big with so many electrons in them, they're very complex. Grade 12 university chemistry. I'll show you how to build those atoms. But if I've got something like silicon in period number 3, I know it's going to have 3 rings. First one's going to have 2, the second one's going to have 8, and the third one's going to have how many for silicon? Just by looking at its position, how many will be in the last ring of silicon? Yeah, generally 4. I can either look up there or I can count my way in from the side. 1, 2, 3, 4. So that electron configuration, that's the word we use when we talk about where the electrons go, is 2, 8, 4. 2 in the first, 8 in the second, 4 in the third. That's simple. The number of electrons in the valence shell, new word, valence, simply means outermost. The word valence comes from a Greek word that means power. And it simply means the power to form bonds. Because in our next note, we're going to learn that it's the outer electrons that form chemical bonds. Those ones that are out there and they're not paired up desperately want a partner to pair up with. And they will take electrons from other atoms to pair up. So the number of electrons in the outermost shell, the valence shell, is equal to that last digit in the group number. Or just count in from the side. Right? Again, phosphorus. 1, 2, 3, 4, 5. 5 electrons in that outer shell. Which means, if I were to ask you to do one more kind of random example, I don't know whether you've gotten that far or not, but let's go with, I can't go too far down, but let's go with chlorine. So chlorine, Cl. I don't even care about the number of protons in the nucleus. I just want you to tell me how many dots to put in each ring, not by counting, but by looking at each of the periods. So if I work my way from the beginning and I build my atom, how many dots do I put in the first orbit? Yep, 2. How many go in the second orbit? How many go in the second orbit? Count across the periodic table. I'm over to here. How many are going to go in that second orbit? Travis? 8. I'm still not even counting electrons. How many am I going to put in the third orbit? How many am I going to put in the third orbit? Parker? Nope, because I didn't make it over to argon in this row. I only made it to here. 7. I'm 7 across. I'm going to put 7. 1, 2, 3, 4, 5, 6, 7. That's a chlorine. We just need the number of protons now. How many protons are in this thing? Yep. You looked at the atomic number, right? Yeah. That's good. That's what I want you to do. Plus 17. So you can see I built that atom without even looking at how many protons or electrons there are. I built it knowing the way the periodic table works. And that was a lot easier. Yes. We'll deal with that in a moment. Okay. So at this point, there's a little bit of homework out of the textbook on these Bohr diagrams. But like I said, I'm going to continue on now talking a little bit about compounds. So you can write that down. I am going to let this save.